Welcome. Welcome to my talk about mastering JPA Performance. My name is Thomas Broell. I'm working for a company named Trivadis. We are located in Europe, mainly in Switzerland and in Germany, but also in other countries in Central Europe. I have quite some colleagues who care about Oracle performance, and we have a few Oracle aces in our company. And some of them talked to me and told me Java, especially Java persistence, is so slow, and from the Oracle perspective, from the database perspective, we could do much better. So this was a reason for me to create this talk. And let's advance to the problem, to the scenario we are facing in our architectures. So typically, we have our clients which are separated from the database by an application server, either let it be monolithic application or a microservice, that doesn't matter. But in a microservice architecture, response times and the performance of your application even matters more, because you get smaller requests, a lot of more requests, and the response time is critical for your user interface. Otherwise, it doesn't feel responsive anymore. So, what happens? Someone tells you, oh, this is a bad performing application. We don't know why, but sometimes users complain. And we have this architecture with the application server in the middle, and we have JPA architecture or JPA interface. Who of you is using or has used JPA in his projects? Okay, that's most of you. Who is confident that this application you created performs well? Oh, only a few hands. Okay. That shows us, in my opinion, how well JPA works, in fact, because JPA is a really nice abstraction for the data access from and maps us from an object-oriented world to a SQL-oriented database. And by giving you this abstraction, you might lose the connection to what is going underneath the API and the implementation. And to walk you through this, I used a test case that's geographic data from Germany. So we're talking about our 16 states we have in Germany, about 6,000 cities, which are related to a little bit more than them, 8,000 postal codes. And these are rather small entities. To create it a little bit more challenging, I added a lorem ipsum text to each of these entities, so just to put a little bit of more data in the database and to see what happens when we use that. So in one case, we have simply those three data fields on the left. So it's the name of the city, the postal code, and the state, which we call Bundesland in Germany, and additionally up to 255 characters of string, randomly generated string. So we walk through these performance issues by using the typical tasks you face. So that's create, read, update, and delete, and we'll cover all of them. Let's begin with creating data. Before you can read or update it, you have to create it. And that's an example, one of the entities I used for this tests. It's just the city entity, which is right in the middle between the state and the postal codes. So on one side, we have this many-to-one to the state, and we have the one-to-many regarding the postal codes. And what I like to do is I like to work with Java and JPA from top down. So I just create the Java objects and let JPA create the tables for me, as well as I use this technical ID, so a generated long ID to identify the entity later on. So that's pretty basic. So this data, it's a Cartesian product in a CSV file. I read it and I just persisted to to the database. So there's a check in between every time a new entity is encountered. So there are only 16 states, but we have 8,000 rows where there is every time a state name and a city name. We need to condense it to the minimum of entities, so it's just 16 states and 6,000 cities. Okay, and this code runs. I tested it on several databases. The code, with the link, you will see it later on, runs by default in an H2 in-memory database, and that's pretty fast. If you bring it to a real database, in this case, I had both of these databases, so an Oracle and a MariaDB. I have both of them in my Docker container running. And you can see the difference. So H2 is pretty fast. If you run the test repeated times, the first executions are actually pretty slow, and they advance with execution to execution. So this is just the JVM powering the H2 database. The other two databases, performance is pretty constant. It stays almost the same if you repeatedly execute the test. But of course, it's much slower because there is a real database in place, which needs to persist the data to disk. And you can see also there is a huge amount of statements running. So it's almost 30,000 statements for H2 and Oracle. And MariaDB needs another ID generator. It automatically used the TableGenerator, and which is responsible in this case for more than 40,000 statements being executed. But if we want to optimize performance, we need to first answer the question, how can we analyze those problems? And there are many options to that. So you can use first the database's point of view. When I get into a project or in a consultancy and face such a performance problem, you mostly don't have the opportunity to change the application. The problem appears or disappears. And you just need to check the environment and get most out of what you get in production, for instance. So there are many options to do that. I mostly, in this case, look on the top statements executed in the database by execution count, not by total time. The normal use case I have, or the normal problem I'm facing in such projects is that you don't see any load at all in these projects. And that's exactly the same in this case. So all systems are running well, they're doing nothing, but the performance is not good enough. So we'll check the statements in an Oracle workload repository report. You can see it, and you can see those numbers, and you can see which statement actually causes this. And in this case, you can see it's some kind select table value from sequence, update sequences, so that's generating those tables, those IDs from a table. The Java developer's perspective is slightly different. You can do many things regarding Java and Java performance measurements. The most simple thing is to use Hibernate show SQL, so simply log all your statements. But if you can't do that, JStack may help you. And that's what I did in this use case. And if you repeatedly execute JStack while your transaction is running, you need to analyze those stack traces. And what I found in 7 of 10 cases was this table generator. You need to read a lot of stack trace, of course. That's what I reduced in font size. You will see in the uppermost line, there's some socket input stream reading from the database, and somewhere below there is this table generator again generating IDs. And the solution to this problem is we just use another generator using an allocation size, which is different than the default. The default is 1, so every time you need an ID for your entity, Hibernate goes to the database and asks for an ID. That's okay for reasonable amounts of objects, but in this case, it's just a lot too much and leads to many, many SQL interactions with the database. So you can just use another ID generator. And for the rest of the talk, I use the TableGenerator because it's portable between all the databases, so it made it easier for me to switch the databases. Of course, for an Oracle database, the sequence generator is the default, and you can add as well there a allocation size bigger than 1. But just for creating portability, I use the TableGenerator. What you lose is the strict ordering of your IDs being generated, especially in a clustered environment. So at some time, the application server needs an ID for an entity. It picks, for instance, 10 IDs from the database. And it's totally indeterministic when it will be using these IDs. So there's no more strict ordering. When you create your entity, you get the next ID, and you can't sort your entities by ID anymore. There's another option to generate IDs. That's the database identity columns. But they are not really a solution for that because there's a JDBC limit regarding this technology, which limits us regarding further optimizations later on. The best ID is the one you get from outside, or you can easily generate, so you can use UUIDs or do whatever gives you an easy identical column. Okay, that's the full-blown Java code. So there is this allocation size of 100, and I tested again using this, and we can see, so H2 stays almost the same. It runs in memory. There's no real interaction. JVM optimizes all the code that is running. There's nothing about it. The first number always is without the text. The second is with up to 755 bytes of text. So, and there is also no real difference if you put a kilobyte of data into the database or not. But we can see there's a massive reduction of SQL statements running to the database, and the performance just improved from MariaDB by factor 10, Oracle by factor 2. So that's quite good, but if you put it on a chart, you can see as performance improves when you increase this allocation size. This is on a logarithmic scale. You wouldn't see it really being a curve on a proportional scale. It would be just, it drops, performance drops on the first 10 points of allocation size and then stays almost flat. So this is an optimization which takes in very fast, but has its limits as well. So just a reasonable count would be 10, and you can see performance or the resulting runtime correlates very well to the number of statements we execute. Yes?
So the question is, the sequence generates a transaction. So when the transaction is rolled back, does it return the same value as the next one?
The question is whether sequence generator is transactional, and the answer is no. Sequences in general are not transactional, and that's even easier for JPA to use because it just can issue a select statement for TableGenerator, which is transactional and requires a transaction. JPA uses a different transaction, so it resumes the current transaction, creates a new one, updates, selects and updates the ID table, or the sequences table, and commits this transaction. So that's a lot of more to do for TableGenerator. Okay, but important is performance improves as we reduce the number of statements. Okay, next analysis, same code, optimized by using allocation size. and we can see a non-batching batch, and this was as well the case in about more than 70% of the JStack outputs I created. I found this line being responsible hanging in this socket read. So it's a database interaction which blocks us. And that's because we don't using JDBC batches yet, and we can enable them, but it won't help in this use case because JPA only supports one open batch. So if you put an entity to the persist method, JPA defers its creation, so its insert to the database, but only as long as the batch is not full and as long as you don't switch entities. So if you persist another entity, or if you issue a statement, a query, it will flush this change to the. So in this case, in this use case, we can have 3 batches to write all the entities to the database. But with our old code, we break those batches several times. So for the states will break a potential batch for the cities 16 times, which doesn't really matter. But the relation between city and postal code is almost 1 to 1.3. So it breaks this batch 6,000 times. And in fact, you won't have any batch anymore. So we need to just optimize a little bit our code. And in this stream operation, I now use a collect. So I get a triple, immutable triple, containing the state, the city, and the postal code. And the code below is pretty much the same. So I check, is this a new object? And persist it if it doesn't already exist. And with the batch size of 100, which is a reasonable number, and you can see it's almost the same chart, it's able to, alone this batch size is able to optimize the same code, almost the same code again. And finally, we are depending on the database, we are 20 to 50 times faster by simply changing a little bit of configuration. So a little disclaimer to these numbers. These numbers were collected on my local machine using databases in Docker containers. It's not a real performance measurement environment. I just did JUnit tests as a repeated test and tried to use reasonable numbers from them. Sometimes it was a little bit confusing because using this long text and not using this text produced sometimes strange results. So sometimes it was faster with the text, which is a kilobyte per row, than without. So those numbers might vary if you execute it on your own machine. So the overall solution in this case is we need to minimize the number of SQL interactions we do to the database. Your physical network, I didn't have a physical network between my server and the machine. It was just running in Docker on my machine. The physical network will affect your performance. And to bring it to a comparable measurement of time, if your CPU runs its clock cycles and waits for the database for 10 milliseconds for a query, that's like if you scale the time and you get your clock ticking like the clock of, on your table, a clock cycle every second, a 10 millisecond wait for a CPU is like waiting for a whole year and hearing your clock tick on the table. So just to give you an impression of about how fast the CPU is and how slow a physical network and SQL interaction actually are. And that's why H2 database is not a good choice to give your developers a real impression of how this application will feel later in production, because they won't have an H2 in-memory database. Furthermore, you're not alone on your network, and reliability matters as well. And if we look at the newly generated workload repository report, you can see there are other statements highlighted, and the numbers of interactions and the numbers of rows modified differ much from what we had before. So, and what we finally did to achieve this batch operations is we sorted our operations by entity to enable batch processing. That's basically what you can do with a little bit refactoring, just to optimize and to get batches running. And what you should do, you should not switch entities. That's what we try to eliminate with sorting, but you shouldn't also run queries in between, flush, or use identity columns, because identity columns are in JDBC are not batchable. Okay, now we created our data. That was kind of an unusual case to write large amounts of data. Typically, application deals with only a few amounts of entities. So, but reading is almost as, or even not more complex. So that's how you find an entity. You can find an entity by query, and you can find it by primary key. And in this case, if you run this statement, it will issue 2 statements to the database. And the one is the one we expect. It selects from the city table. But Hibernate tries to give you an object for the city you select. And this city object consists of several fields. One of it is the state. And to give you an object, it just selects additionally the state you need. And that's called the 1 plus n problem. So you have one statement in the code, and Hibernate effectively executes n statements. It depends on your data, it depends on your model. And it doesn't take care about those too many collections, but all to one relations. So if you persist an entity, typically you connect it to your master data. You have lots of master data connections, and all these entities are fetched by single SQLs. Okay, so there's a demo project. The link, you get it on the last slide. I'll show the code running. So what's relevant for this case is first, you can do a so-called, I call it database ping. We just use JPA to run a query against the database without any results, and I measure how long will it take on average. So it runs 100 queries. We can see them. And the average time for such an SQL interaction is about 1 millisecond. So we can use entity manager.find to find an entity by its primary key. And this will cause one statement only. And there's only a where clause on the city ID. There's no state selected. And this actually depends on, there's the left outer join. So Hibernate joined it. In this case, it joined it together. So we get 2 entities with one query. This depends on how you map your relation. So this relation to the state may be mapped as many to one by default. So you leave it to the provider how it is selected, and you can have it eagerly and lazily loaded, but all these fields are just hints to the provider. It doesn't need to respect it. So just You need to test it, and that's what I do here. So I can use the Hibernate statistics and assert whether the expected count of loads and fetches matches what I expect. This mapping, which we do in the entity, isn't respected if you run a query. So in this case, that's what I showed on the slide. In this case, we get 2 selects, one for the city and one for the state. So the query results in one city, and in the city there's a foreign key to the state, and Hibernate fetches this. You can mark it as lazy, then you can prevent this additional statement. What you can do in your query is you can left join fetch the state, which results in, let's bring up the result once again. So using Hibernate statistics, you can get the time out of it, and this is 2.9 milliseconds. 2.9 milliseconds. It's given in nanoseconds. So the reading those 2 entities is 2.9 seconds. When we do it with a fetch query, it should be faster. So it's 1.7 milliseconds. So just, if you know which data you need, just mark it as lazy, fetch the data you need in the query. With JPA 2.1, there is an additional API, a graph API, where you can put it in the API which entities you select. I prefer writing those JPQL queries because you can read them perfectly. Okay, so let's advance. I have a collection of postal codes, and I want to read them. And what I do is I just take the stream of my postal codes, I flat map them by reading the object by code, so it's basically a query, and collect the results. That's the worst example you can imagine for this use case of finding some entities, and you can see why. So it has run already 10 times or 5 times. So that's the number of SQL statements we execute to the database. And the time we spend for that is 20 milliseconds, just for executing those 17 statements. So that's 2 years in your clock being 1 second for each cycle. So what I do here is I assert all the query results and the executions. What you can do instead is you can write a query which does not query one postal code, but use an in statement, and you can just put this collection in the in statement. When you run this, that's postal codes better. Okay, we have just one statement running with this in clause, and apparently we just fetched one state. So now I just used the same code with another collection of postal codes. That's the bad one. So it was the same code, and as you can see, the resulting queries on your database, they highly depend on the data you feed in and the relations your objects have. So that's why sometimes those performance problems appear as, we call it Heisenbug. So if you look at it, it disappears. So if the developer goes to the customer or to the user, they can't show them the problem. They don't know why did it yesterday not perform well. But now we look at it and it does perform. It's not because the system is performing bad, but because it's highly data dependent. Okay, what can we do in this case? In this case, we can use Hibernate to trick a little bit, and that's in this method here, postal codes optimized. I just run 2 queries, and I discard the result of the first query. Hibernate caches those entities and will use them as a reference for the result of the second query. So let's have a look at those queries. They are both defined in postal codes. So the prefetch query is, I select the state. So at maximum it can be 16 objects, but it's still an SQL interaction. And I use the same where clause as I do for selecting the postal code objects. And I select the postal code objects fetching the cities. So I know they're almost one-to-one, so fetching a postal code might not be too costly to get the city as well. Of course, if the postal codes are all in the same city, you get duplicate results for the cities. It's a Cartesian product. It's a little bit larger than it should be. But this optimized code, we will run it. This optimized code runs always and totally data independent in 2 queries every time. Just depends on your database performance that this performs well. And we're back to 7 milliseconds for both interactions. So to stay on deterministic and to not depend on your data, you can use these queries to optimize your data access. There's basically, the slides are just for your reference. I showed you the code. The code is a mainly JUnit driven project. There are only the entities in the real code. Everything is in the test cases. Yeah, so this is this left join fetch. So we explicitly use eager and lazy. We fetch those entities in our queries. That's the point where we can manipulate and we can, for our specific transaction, optimize what data we fetch for performance means. It's the power of the in clause, which enables you to deal with multiple entities and to run your queries and your transactions for more than one entity. And the prefetch query, yeah. What also improves the performance a little bit if you tell the database and JPA that you don't need all the data which is in the database. So you can just use this first and max result methods, and the result will be limited in the database. So nobody uses the second page of Google results, so why should you load it? But overall, if it's not a table with millions of rows or thousands of rows, it has a small impact to your performance. Okay, updating. Updating entities in JPA is kind of automagic because you just fetch those entities and apply setters to them. And what Hibernate basically does is it updates those entities on transaction commit or if any flush happens. So flushing entities is what Hibernate does to synchronize its in-memory entities with the database. And this happens, the latest point is at transaction commit, but there are many other points in time where this can happen. So if you switch operation, for instance, if you insert or delete something, if you issue a query or explicitly flush your entity manager, everything gets written to the database. And as often as you do that, this will run everything which Hibernate requires to do that with your entities. So it will perform dirty checks on all your entities, and do possible database updates. And this matters when your entities are large or when your persistence context gets large. So if you have thousands of entities, every time this persistent context gets flushed, you perform those dirty checks and updates on all the entities. Another possibility, I don't know in which version exactly it appeared in JPA, when you want to update a foreign key, for instance, we assigned it the city to the wrong state, we need to update it, but we don't really want to select the state from the database because we know it and we know the primary key of it. We can use entity manager get reference. What you get from it is a lazy initialized proxy to the database instance. And you can use it, you can assign it to the city, and it will cause no select on the database. It just updates the city. It relies on database integrity. But if you touch any field of the state, so if you ask for its name, of course, Hibernate will cause a select and execute whatever you need. Yes?
This is the standard in JPA?
This is JPA standard, yes. Okay, flush and clear. Interestingly, you won't need them really for your application. Flush and clear are typically only valid together, except for your test code. So I use it in my tests just to get the statistics out of Hibernate, how much it does for a transaction. Basically, flush does all the work needed to synchronize your memory with the database, and clear makes Hibernate forget all managed entities. That's what you need if you persist large amounts of data you don't want to keep in memory anymore. But interestingly, these two lines of code lead me mostly to transactions which are performance critical and where the developers thought this would help in performance. So you don't need it, and it doesn't help at all, except you want to clear up your memory with clear. Then you need flush in advance. Okay, deleting entities is pretty straightforward. There is not much about it. You can remove an entity when you have it in your hands. That sadly doesn't work with references. I think it could, because if the database tells you, hey, there is no entity I could delete, it could still fail, but it doesn't. You can delete by query. And what annoys me the most is if you create your database model top-down, there is no index created for the foreign key. When deleting, the database always asks, is any foreign key referencing this entity? So you need to create this index on the database tables by hand. This would be a minor improvement, yes. But you always should take care of your index in the database on yourself. So that's basically the two ways to delete entities. Just to have a little bit of fun, I thought I will move my database to the cloud and check what happens if I do that. And I ran this database ping in various cases. So I had the application server in the US and the MySQL database in Europe. And I had it in the same data center. So in the same data center, this database ping was 1 to 2 milliseconds. Crossing continents, it's 120 milliseconds. And in this week, I measured in the Wi-Fi of my hotel, which is surely not a good network. But I had 140 milliseconds to a MySQL instance in Europe. Just to recall, the speed of light is limited in glass fibers. It's slow compared to vacuum, so it's just only 200,000 kilometers per second, but it still matters. So the physical limit for interaction is 80 milliseconds. and I ran the same code with the same optimizations, and I came out with 54 seconds. So I didn't take care about what database it was. It was a relatively poor performing instance. What do you think? How long will it run without dispatch performance optimizations? So just batch level, one row. Who thinks it runs within the first 5 minutes? A few hands, okay. 15 minutes, up to 15 minutes. Okay, a few more, up to 30 minutes. Okay, longer than 30 minutes. Okay, not all hands are working anymore. Actually, I got 35 minutes for the same code. So that's just to give you an impression how much latency to your database matters to the performance of your application if those optimizations are not in place. And another thing I got out of this is you should take care of your JDBC driver. Last year I did this with the MySQL JDBC connector, and at that time that was really bad because it did batches, but it wrote every single statement as a SQL statement to the database. I Wiresharked the protocol to see that. Today the up-to-date connectors are much better, but for instance with an Oracle database there is a parameter to optimize fetch performance. By default, the Oracle JDBC driver only fetches 10 rows. And if you go to the result set and need more, it does another round trip to the database. So there might be some hidden tweaks where you can optimize your driver. So that's custom options. Okay, a few words more on caching. If we place put caching in place, we just add an additional layer of hidden data between our application server. And if it's a cluster, we should think about how to synchronize this data. So potentially you need some kind of a distributed cache. And there might be other systems accessing your database, so you should check if this scenario is valid for your application as well. If you go in caching, and there's the two most common misconceptions about caching is easy and it solves your problems. Caching in the first place gives you a lot of new problems. So you can totally prevent SQL statements being executed, but you should use it for data which you need often, which you read often, and which you rarely change. Because changing data in caches will result in those memories need to synchronize, and finally you need to configure all this, and you might end up being eventually consistent in the result. But how does it work? There are 3 caching modes or 3 caching levels. We use the first one, that's the first level, that's the entity manager, your persistence context. We used it as a cache in our prefetch query with those postal codes, where I just executed a query to get those entities in the persistence context. There's a second level cache, which will which we can get entities from over your transactions, and there are three of them. So there's an entity cache, basically a cache per entity name, which caches the entity data by primary key. There's a query cache, which caches the resulting entity IDs based on the query itself and the query parameters. And you have this collection cache, which you need to enable, where you can, for instance, have for a city with an entity and a role name. The role name would be the postal codes of the city, which caches then the list of all the children. So all postal code IDs it got from the database for a specific city. So it really works well, but you should take care and if there is a cache in place or flush in clear, so some kind of alarm clock runs in my head to that. So conclusion, you can calculate your performance with this formula. If you have a takeaway from this talk, just focus on this n being constant, so that the sum, the total time of your transaction is the connect time plus all those equals and the connect and the commit. Here are some links, and this is the link to the source code of my demo project. I'll take questions in the hall or right here in front. Thank you very much.